Well, hey there, everybody. Welcome to week 4. So we are getting there. We're almost halfway through the course already. So I think this week's chapters, as you see, so chapters 9 and 10, get to some, really more important information. I guess maybe important is not the right word, but more of the detailed information about quantitative statistics that sometimes feels a little bit scary. But if you can reasonably get a handle on the information presented in 9 and 10, then I think you're a lot further than what you probably realize to understanding statistics, at least from a consumption side, at least from being able to, read a research article and kind of have an idea of what it says. So the first chapter not the first, but the chapter 9, the first of the ones we're looking at today, is on probability and hypothesis testing. And so this is what comes up all the time in research. Okay, so, oh, by the way, neither of these chapters fully explain, either of these concepts, but step you into it, I think, in a really nice way, in a very understandable, basic kind of way, so that you can start building on that knowledge. That's the purpose of these two chapters. So it's not super overwhelming in jumping into this. But I think if you have this basic understanding, I think it's going to be super helpful for you when you, not just for this class, but more importantly for, after this, when you're reading or hearing about research. So when you hear a comment like that it was, significant. So let's just use an easy example, like taking a blood pressure medication is going to significantly lower your blood pressure. Okay, so something as easy as that. What does that mean, significantly lower? And when people use that language, or sometimes they use statistically significant, and we'll look at maybe what that means, the differences there here in a minute. But what it means is that there was some type of research study that was done, there was data that was collected, and it was analyzed to show that there was in fact a difference before taking the medication versus after. And so did that difference rise to a significant difference relative to statistical tests that were done? Or did the difference rise to a clinical significance, which there, would be a difference there. We'll talk about that in a minute. So a practical difference, like a clinical significant lowering in blood pressure that made a difference for the patient or not. And so this is really what we're talking about, is understanding those types of statements so that we get an idea, okay, what does it mean to say it's statistically significant difference? Okay, so getting into this hypothesis test. So a lot of times we'll say, oh, I hypothesize that if I run 30 minutes every day, that my fitness level will improve. Okay, so that's a hypothesis. And a lot of times that's how we're used to saying a hypothesis statement in that way. But I think it's important to realize that, and they have a sentence in here that says, all research decisions are made within a certain probability of being right or wrong. And what that means is that you cannot 100% say that you're right or 100% say that you're wrong. That there is a probability in that statement that you make, that there might be a small chance, hopefully, but a small chance that, I conclude that my fitness level is going to improve, but there might be a small chance of saying that I'm wrong in saying that, okay? My conclusion is wrong. So there's always that chance, and this is what we're talking about mostly in this chapter. If you get that concept, and I think you're quite a ways there, because we use some language that, or I'm loosely using but we use language to explain that probability there and how I might be wrong in my conclusion. Okay, so and probability and I know you've seen this when reading research, but is the lowercase p. So that's what the p stands for, is probability. And so you'll see probability equals, or probability, or the letter p, less than or greater than, and then a number behind it. We're going to talk about that in a second, but that's what essentially that means. So that, almost every research study that you see has that, that small p in there. Okay, so when you're doing hypothesis testing, and this is where statistics kind of gets a little challenging, is that there's new language with learning something new like statistics. And so sometimes the language is difficult to wrap our heads around, and that's what throws us off. But the null hypothesis, okay, so there's a null hypothesis and an alternative hypothesis. The null hypothesis simply means that there is no difference in the relationship. Okay, so that if I run every day for 30 minutes, that the null hypothesis would be there's going to be no difference in my fitness level from running every day for 30 days, for instance. That's the null hypothesis. The alternative hypothesis would mean that there was a difference, and that difference was real, okay? And in order to say in your experiment that the difference was real, I'm going to include a little caveat that says I might be wrong in that statement, and that there might be, I might be wrong because the difference, the real difference that I think is happening, might be just due to chance, okay? It might be what they call a sampling error. And so I might be wrong in that conclusion. But what's my acceptance of me being wrong? Okay, so this is the decision every researcher needs to make. What is this error of chance, my acceptance of it being due to chance? How comfortable do I feel with that? Do I feel like there is a 5% chance that I could be wrong, or a 1% chance that I could be wrong? And this is essentially probability. Accepted level of, generally across the board, an accepted level of probability of being wrong is 5%. Okay, so you don't want to be wrong 50% of the time. That doesn't have a lot of credibility there. You don't really know what decisions to make based off of that. But if you can say that if I go running every day for 30 minutes for 30 days in a row, that my hypothesis is that my fitness level is going to improve after 30 days. And I'm going to accept a probability that I'm wrong in that statement of 5%. So a 5% chance, the 5% that the difference that I see in fitness level between baseline and 30 days is due to just sampling error, chance alone. Okay. But you could also say that, well, I'm pretty confident that that this is going to happen, and I'm going to put that probability level to a 1%, and that would be, I'm even more confident, okay, that that the difference that I see in fitness level after 30 days is just due to chance. I think it's due to a real change, which would be running, right? That the running is doing something to my aerobic capacity, my muscular strength and endurance, my heart efficiency, that it's going to improve my fitness level. I think there's so many variables in there that are going to improve my fitness level that I don't think that it's going to be due to chance alone. And so I might set my my probability level to a 1% chance, for instance, that there is going to be a real difference that we see, and I feel pretty confident about that. So that would be, the level of significance. So say you did this experiment that we're talking about, and that you ran every day. So let's say you got a group of people. Let's say they were 20-year-old healthy adults, and you put them on a running program for 30 days, for 30 minutes a day for 30 days. And at baseline, you measured their aerobic capacity with a fitness test. And then at the end of 30 days, you did the same test, you repeated the same test, and then the aggregate or the average, the numbers of all of your people that were in your program at baseline. You have an average aerobic capacity at baseline, and you're going to compare that to the average aerobic capacity at 30 days for the group in each, not individual of all people in the program, but group combined together. So this number versus this number, is there a difference between the two? Okay, so maybe let's just use easy numbers. Let's just say the aerobic capacity, let me just make up numbers, right? So the aerobic capacity at baseline was 2, and the aerobic capacity at 30 days was 4. Okay, so there's a difference between the two. You went from 2 to 4. Is that difference statistically significant? Of course there's a difference. You showed that aerobic capacity changed between baseline and between 30 days. But was that difference real? In other words, could it be that the people you chose to be in your study, there was something unique about them, that they were going to improve aerobic capacity, fitness level, no matter what, over those 30 days? Okay, so maybe there was something of a sampling error. Maybe you picked people who have to walk to school, and those 30 days just happen to be the first 30 days of the school year. And so maybe there was a sampling error that you just didn't pick the right people, or that it didn't represent people from the community at large, that there was something unique about them, that aerobic capacity was going to increase anyway. That's a possibility, right? But what we're thinking is going to happen is that anybody who's put on a running program for 30 days is going to increase their aerobic capacity from baseline to 30 days. What you're doing in your statistical test is being able to say that with a certain amount of confidence that in fact the change in aerobic capacity from 2 to 4 was due to a real difference. It was due to the running program itself, okay? And so that's what you're trying to show with the statistical test that you're running. If you can wrap your head around that concept, then you're a long way forward in understanding research and the statistics that they use. Okay, so if it says that we ran a statistical test, and it talks about which statistical test that was done in here, and we're going to talk more about that. It gives examples of which tests to run, or what's there's multiple tests that you can run that would show if there was a difference there, depending on the circumstances of the research experiment. And this is where it comes down to, how do I know what test to pick? What statistic to run to show if there was a real difference there? That's a conversation for a different day. But if you, so say you pick the right test and it shows the difference there, and it comes up with a p-value, okay, so probability value, but we're just gonna call it p-value from now on, that the p-value that you decided to set was if the p-value is less than or equal to 0.05, then I can conclude that the difference between 2 and 4 was real, and that it is with a certain amount of confidence, a p-value, I am confident at a p-value of 0.05, that the running program improved fitness level. Okay? So running a statistical test will give you an actual p-value, and you will then compare that to, is it less than or equal to 0.05? If it is, then I am concluding that it is not due to chance, it's not due to the sampling error, it's actually due to a real difference. Okay, so I think that's the main point to get. And there's a lot of other pieces of information that are really important with all of this in how you go about doing that. But essentially, that's probability testing. And if you can wrap your head around that, then that's great. So then there's talk about, a two-tailed test versus a one-tailed test, and what makes sense to run when. And so in the example I gave you, you would probably want to run a one-tailed test because you are pretty certain that aerobic capacity is going to improve based on previous research, that you already know this is probably going to happen. But if you know that the outcome that it wouldn't get worse, right? That aerobic capacity or fitness level wouldn't decline because of doing a running program, then you're certain that you're going to be on one end of this normal curve, okay, on the one-tailed end of it. If I didn't know that it was going to be on one or the other, that it might decline or it might improve, I don't know, then you have to pick a two-tailed test. But if I know that a running program, I'm pretty confident that's going to improve fitness level, then I'm going to pick a one-tailed test. And that's the difference between two-tailed, one-tailed. Just for an example, this is how we did, the risk reduction program when we were doing our statistics for that on baseline versus 1 year, that we were pretty certain that that our program was going to, improve fitness level, but I wasn't very certain if it was going to improve weight loss. Okay, so we had to run a different statistic there. So I was pretty certain that our fruits and vegetable intake would improve, but I didn't think it would decline. Okay, so it was one-tailed versus two-tailed. We would pick a one-tail on that. But, I wasn't very confident that we were going to actually be able to lose weight across the board. And in fact, some people didn't lose weight and some people even gained weight. So we had to run a two-tailed test on that variable. But, not all variables made sense to do a two-tailed. It made sense to do a one-tailed test on fitness level, for instance. Okay. As it did for them adhering to taking their medication, because we were talking about it so often that I was pretty certain that they would not go backwards in taking their medication and not decide not to take it. They would actually be more adherent to taking medication. So that was a one-tailed on that too. So that's just some information about how we did that particular program. Okay. So I think that's the most of the important part I want to talk about on Chapter 9. Chapter 10 gets into relationships and predictions. Again, a really important and often used statistical evaluations for various types of programs. And this really is based on correlation. So can you say that two variables are correlated? If one happens, is the other one happening also? And so before I get ahead of myself, it's important, I think, then when you're looking at diagrams, like they have a bunch of them in Chapter 10 of scatter plots, and you see them often, or sometimes you don't see the scatter plot, but you just see the trend line, that we understand that, a couple really basic things is that if it's moving in a left to right upward movement, that it's a positive correlation, or if it's going upwards in that upward trajectory, or it may move from left to right in a downward, and that would be a negative correlation. Don't go there of thinking that one is good and one is bad, because that's not certainly the case at all. And there gives a lot of examples in here as to why that is. One of the things that's really important to realize when you're looking at correlations is it's not necessarily a cause and effect, and oftentimes it's not. They say it in here a couple of times, but I really wanted to emphasize this again, that a lot of times researchers make mistakes in looking at that because two variables are correlated, that let's just say graduate students, people who are in graduate school and grade point average, those two things, as I think I mentioned last week, are correlated in that grade point averages are typically higher for people who are in graduate school. And so you sometimes see this, on a graph where the longer you go to school, that the grade point average continues to increase, and that's a correlation. But it's not a cause and effect. It doesn't mean that grad school produces higher grade point average, and that just because you're in grad school, you're going to get a higher grade point average. We know that that wouldn't make sense. So it's not a cause and effect, but rather just a relationship. It's only correlations only talk about relationships, not cause and effect. And so we have to be able to differentiate the two of those. So a lot of what you hear are Pearson R correlation. And so that's the super common one. You then, if you can, understand what the book is getting at relative to that's your, statistic you can use. And the strength of the correlation, I think, is also a very important piece to understand here, in that based on the size of the R, so lowercase r, that the number that you get of that correlation statistic, I do the R, correlation statistic is tells you something about the strength of that relationship. So they give really good cutoff numbers for this, and this is helpful to know. It's part of, really part of your understanding reading statistics if you kind of know these, but anything that's 0.25 or lower is a weak correlation or a weak relationship. 0.26 to 0.5 is moderate, 0.51 to 0.75 is fair, and anything greater than 0.76 would be considered a high correlation. So a lot of times you'll read that these two variables are highly correlated, and that means that their R value is a greater than 0.76. Okay, so this is where we use statistics to know how highly correlated or how close that relationship actually is. And so that's an important part of that part of understanding correlations there. The other part to this too that I think is probably worth mentioning is the regression analysis. It comes up a lot when we're looking at statistics. And so when you have a whole bunch of variables, and you can say that that somebody, let's just pull this out, and we didn't, okay, so this is a good example. So in our cardiovascular and diabetes risk reduction program, and it may be something that you think about in your program too that you design, that we had a whole bunch of variables that we were doing at the same time. And what our ultimate goal was is to reduce cardiovascular risk. We could have done this if we had enough people in the program, but we didn't, so we didn't have the statistical power to run this type of test. But we could have done a regression analysis on multiple variables to show that all of these variables together show a decreased risk for cardiovascular disease. And within that statistical test, we could eliminate certain factors that might confound our ability to see if it was what we were doing in the program or something that was just happening within the population that we had. So sometimes you can, not sometimes, but something like this where you have all of the interventions we're doing in the cardiovascular and diabetes risk reduction program. If we wanted to take out something like education, we could. So it's not something we do in the program, where of course we're not, granting degrees and educating people, but just people who are in the program are more highly educated because we're doing it at a university setting. So most people had college degrees, and most people had, advanced college degrees or a doctoral level and so forth. Or a clinical level, whatever. But we could, if we had enough people in the program and had enough power, statistical power, to run a regression analysis, we could say that people in the program, just for instance, are reducing their cardiovascular risk because of the interventions in the program, and we weeded out, and not because they were more educated and could figure it out on their own, for instance. Okay, so that's something that is talked about in the book here when we're talking about let's see, multiple regression analysis, and within a multiple regression analysis, you can do a partial correlation, and that can then take out some of these factors that might be confounding your conclusions. So again, this chapter and the previous chapter is just getting to a baseline level of this and just kind of understanding some of this language in here, so that we have, you know, a bit of a handle on what it means when we read that they were statistically correlated or highly correlated. There's a statistical significance between this and that. There's so much, you know, of course, that could be, you know, talked about here, but I think that's a good place to stop with this information, and that, you know, I think relative to this class, if you can wrap your head around those things that we've just talked about, but, you know, the major concepts that are in chapters 9 and 10, I think you are going to be a long way forward in understanding statistics when you read them. As we mentioned before, doing statistics yourself, being an independent researcher where you're doing your own statistics is another thing. And I, you know, disclosure, I talked about this before. I consult with people who are experts in this to make sure, you know, I'm picking the right tool. I'm setting the levels where they should be, you know, as far as significant levels, where I think they should be. And then when we get it back, that I actually am interpreting it, you know, correctly in that way. I think that's a good thing to do, but at least I'm in the ballpark of understanding the language to a certain degree, and you know, feel a certain amount of confidence that the test is done correctly. So anyway, looking forward to, again, what you have, you know, coming through as far as assignments this week. If you have any questions, just let me know. Thanks.